All right, here we go. Next video in chapter 12 is a two-parter. Well, covering two sections, I guess. This one should be shorter than the last one. All right, so we're going to talk about torque and angular momentum. So here we go. All right, so let's get this thing out of the way. All right, so angular momentum. So forever ago, we learned a moving object has momentum, right? And I guess I should stress the fact that it's a vector, right? So momentum as a vector is mass times velocity as a vector. Please remember that your momentum and your velocity are always in the same direction, okay? Similarly, a rotating object can have angular momentum. Again, these are vectors, so your angular momentum is, analogous to your linear momentum. Mass is analogous to rotational inertia, and linear velocity is analogous to angular velocity, okay? Again, technically, these vectors have linear direction determined by what is called the right-hand rule. If you take more physics later on, you'll learn it. I'm not worried about it. We're just going to stick with clockwise, counterclockwise. Again, as usual, counterclockwise is positive, clockwise is negative, all right? Excuse me. All right, now, angular momentum only has meaning with respect to a specified origin. Maybe more to the point, a specified pivot point, right? Just like torque. Okay, when we talk about torque, we talk about the torque about some pivot point. Some axis is probably the technical term for that, right? Similarly, angular momentum only has meaning if you specify what the pivot point is, what the axis of rotation is. All right. Now, in the same way that your linear momentum is in the same direction as your linear velocity, your angular momentum is always in the same direction as your angular velocity. Okay? So, there's not a whole lot to that. I'm not actually going to do a straight example where we just calculate angular momentum. Instead, I'm going to jump into conservation of angular momentum, and as we do that, we'll do a couple of these calculations, all right? Yeah, so let's just do it, all right? So before we do our example, I want to take a quick second. This is probably a good time to take a moment and compare all of our linear and angular velocities, or linear and angular values, okay? So the big thing I want you to notice is, like, I don't really memorize the angular values. I memorize the linear values, and then anytime something angular comes up, I just use, I just think about what the linear counterpart would be, and then translate it over, okay? So, momentum is mass times velocity, mass is inertia. Angular momentum is inertia times velocity, okay? So it turns out, if your net force is constant, your change in momentum is equal to net force times time, right? And that is, again, the same as mass times change in velocity. So those same equations work angularly, okay? If your net torque is constant, then your change in angular momentum is inertia times change in angular velocity, which is the same as net torque times time, right? Because the angular counterpart for net force is net torque, okay? And all the same calculus rules work. You can integrate net force with respect to time to find your change in momentum. You can integrate net torque with respect to time to find your change in angular momentum, okay? Newton defined net force as the rate at which your momentum changes. Similarly, net torque is the rate at which your angular momentum changes, okay? Newton's second law says acceleration is net force over mass. Angular acceleration is net torque over rotational inertia. All right, I'm going to add a couple down here, actually, to the list. We know that kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. So let's talk about work, right? Work is a change in energy, right? So work is basically force times displacement, right? If your force is constant and blah, 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 blah. So similarly, work is equal to torque times delta theta, okay? And if you ever have to integrate, work is equal to the integral of force with respect to position. Similarly, work is equal to the integral of torque with respect to theta. In our work kinetic energy theorem, net work is our change in kinetic energy. Over here becomes a net work is change in rotational kinetic energy. No, I don't like that. This still applies, where change in kinetic energy is the sum of translational and rotational kinetic energy. Okay? Yes, final answer. Okay, kabam! So, that's a super quick crash course. If you want all of your physicsy equations, that's a whole bunch of stuff there, right? Okay, so, kabam, kaboom, let's do an example. No, we can't do an example yet because we need to learn about conservation of angular momentum. All right, so when we learned about linear momentum, we learned that in a closed system, in other words, if there are no external forces acting on your system, then an object's total momentum remains constant. And we wrote that this way. Total momentum before the collision or before the explosion is equal to the total momentum after the collision or explosion or whatever, right? All right, so similarly, this time we are going to have conservation of angular momentum, which means that the total angular momentum before some interaction of some sort is equal to your total angular momentum after, okay? The classic example of this, and we'll do this in class again if you guys remind me, there's a lot of that in this chapter, is a figure skater pulling her arms in, right? So check it out. Angular momentum is I times omega, right? So the idea is when your figure skater is spinning, so here's a figure skater. So right now she's spinning around with some angular velocity. She's got her arms out right now though, right? So right now she's got a large amount of rotational inertia because she's got mass kind of far away from her axis of rotation, and so she's spinning relatively slowly, right? So then what happens is if the figure skater pulls her arms in, again over here, what happens is they suddenly spin very fast, right? And the reason that happens is when they pull their arms in, they're bringing their mass closer to their axis of rotation and thus reducing the rotational inertia, okay? But there are no external torques, right? Because all of the force is in towards the middle. And so the angular velocity increases, okay? All right, this also works for collisions, okay? So I'm going to do an example here that covers both bases, all right? So this example hits a number of important points, okay? So there's a lot going on with this example, all right? So here we go. So on a playground, there's a small disc-shaped merry-go-round with a radius of, let's write down and give it information over here. So the radius of the merry-go-round is 1.2 meters, and the mass of the merry-go-round is 160 kilograms. It is disc-shaped, and thus I is going to be 1/2 mr squared. So if you plug your numbers into that, the I for the merry-go-round turns out to be 115.2 kilogram meters squared. Okay. Okay, let's see. Sally has a mass, so this is all the merry-go-round. All right, Sally has a mass of 40 kilograms and an initial velocity of 4 meters per second. No, 3 meters per second. I apologize, I can't read. 3 meters a second. All right, initial velocity 3 meters a second along a path that is tangent to the rim of the merry-go-round, and then she jumps on. All right, the merry-go-round, oh, we're back to the merry-go-round. Who wrote this problem? So the merry-go-round was initially spinning towards Sally with a period of 8 seconds. Oh, man. All right, period is 8 seconds. I don't know why I wrote this way. So we can find our corresponding angular velocity, right? Angular velocity is 2 pi over t. So 2 pi divided by 8 gives you 0.785 radians per second. Okay. Let's see, and we're going to neglect friction, blah, 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 blah. Okay, so we got to find the initial angular momentum of the merry-go-round, initial angular momentum of Sally. So this is weird. Angular momentum of Sally, she's running. She's just gotten, well, you would think she just has linear momentum, but it turns out we can also treat her as having angular momentum. So I'll get to all of that in a minute. All right. Before we do, it is probably worth our while to make a drawing. All right. So here's the deal. So here, top view, here's the merry-go-round. Here's Sally running tangent to it. Okay. And so the idea is I know her velocity is this way at 3 meters a second. And the merry-go-round is spinning towards Sally with an angular velocity of 0.785 radians per second. Okay? So this is kind of a collision, right? She's going to, in essence, collide with the merry-go-round. And it looks like probably slow the merry-go-round down, right? Doesn't that kind of make some intuitive sense, hopefully? Okay. So the idea is once she hits the merry-go-round, she's going to start rotating. So the axis of rotation that we're interested in is about this pivot point. So I'm going to use capital P for that. All right. And so when you measure your radius, well, I'm getting ahead of myself. Okay, so that is that. All right, so let's do some stuff here. So, cool. All right, so A wants the initial angular momentum of the merry-go-round about its axis of rotation. So A, we want to find the angular momentum of the merry-go-round initially about its axis of rotation. So L is simply I omega. So, well, that's not too bad. We already found our I. That's 115.2 kilogram meters squared times our omega. That's the 0.785 radians per second. So multiply that out and you get 90.5 kilogram meters squared per second. All right, please notice units for angular momentum are not the same as units for linear momentum, any more than units for torque are the same as units for force. All right, the next thing we need to talk about probably is the sign. Notice in my drawing, my merry-go-round is rotating, clockwise, which means the angular velocity is negative, which means my angular momentum is negative. That is a really big negative sign. Okay, so that's that. All right, now Sally. All right, so here's the deal. So Sally is kind of a point particle, right? And so what we're going to do is we are going to do this. So the angular momentum, this is part B. Angular momentum for Sally initially, well, that should be I times omega, right? So it turns out that her angular velocity, when you do this, it's v times r, but you have to measure your radius. This is a thing that has never come up before. Your radius has to be perpendicular to your velocity. So the radius is exactly what you would expect it to be. But notice, you do not need to measure this sort of hypotenuse there, right? Because at the instant at which she collides, the distance that she is away from the pivot point is just the radius of the merry-go-round. But it turns out, even back here, her angular momentum is still the same, okay? So here, your radius should be perpendicular to your velocity, okay? So, let's see. So I, she's a point particle, right? So I for a point particle is mr squared times omega. We don't know omega, but we do know her velocity. And velocity is v over r, okay? So that means that the angular momentum of Sally is, notice the r's cancel, and you get this, mvr, right? So this is a very common equation worth writing down. That is the equation for the angular momentum of a point particle. Write it down. Angular momentum of a point particle. Sally is a point particle. That is the equation. All right, so here we go. Let's find her angular momentum. It is 40 kilograms worth of mass, right? Isn't she 40 kilograms? Yep. Times her velocity, 3 meters a second, times the radius, the perpendicular distance away from the pivot point, which is 1.2 meters. So multiply this out, and you get 144 kilogram meters squared per second. and this time positive, right? Because she's contributing to motion counterclockwise, right? Okay, so that is parts A and B. Let's make a note of what we just decided over there. Angular momentum of the merry-go-round initially is negative 90.5 kilogram meters per second squared. Angular momentum of Sally initially is positive 144 kilogram meters squared per second. Oh, I guess I should actually that. Okay, squared per second. All right. Okay, so that is that. Now, so all of that was just calculating angular momentum. All right. C and D get into conservation of momentum. Conservation of angular momentum, to be specific. All right, so C wants to know what is her speed after she jumps onto the merry-go-round. So there's this sort of collision between Sally and the merry-go-round, right? Once she jumps onto the merry-go-round, they're going to have the same angular velocity, right? They're both going to be rotating at the same angular rate. Okay, every time Sally goes around once, the merry-go-round goes around once. So they have the same angular values. Okay, so to do part C, here's what we're going to do. Part C, the total angular momentum before Sally hits the merry-go-round is equal to the total angular momentum after Sally hits the merry-go-round. Okay, well, the total angular momentum before she hits the merry-go-round is just the sum of these two guys. So that's negative 90.5 plus 144, right? Okay, that's got to equal the total angular momentum after. So that's equal to the angular momentum of the merry-go-round afterwards. So that's, let's write this out in steps. Angular momentum of the merry-go-round afterwards plus angular momentum of Sally afterwards, right? So angular momentum of the merry-go-round is I, 115.2 kilogram meters squared times some omega, plus the angular momentum of Sally. So I could write MVR, right? That was what I just said. Write that down. Angular momentum of a point particle, right? But this time I'm not really interested in V. I'm interested in omega. All right, so I'm going to write her I as mr squared. So her m is 40. Her r is, she's 1.2 meters from the center of the merry-go-round. Don't forget to square it. So that's her I times the same omega as the merry-go-round, okay? So this gives us 115.2 omega plus 40 times 1.2 squared is 57.6 omega. So that gives us 172.8 omega equals this mass, which is what, 54.5? Is that right? About 53.5. I think I did my calculations with 54, so my answers are going to be off by a scotch. So anyway, if you divide this, your angular velocity after the collision is 0.3125 radians per second. Notice it slowed down just like we thought it would, right? And so then her velocity is, well, we got to use a jumper, right? So 0.3125 times her radius, which is 1.2. And so that gives you 0.375 meters per second, right? Okay, so that is a conservation of angular momentum problem that dealt with sort of a collision, right? We had these two objects interacting. The only torques are the torque of Sally slowing the merry-go-round down and the torque of the merry-go-round slowing Sally down, right? So we lost energy here, right? Because both objects slowed down, okay? Which makes sense, right? Because it's an inelastic collision, okay? Perfectly inelastic, I should say, because the two objects stick together. All right, now part D. So right now, Sally is sitting at the very perimeter of the merry-go-round. All right, so what would happen if she crawled halfway to the center? Not all the way to the center, but halfway to the center. So this is kind of like the figure skater pulling her arms in, right? We're moving our mass closer to the center. So this isn't so much about two objects colliding anymore. Now it's about redistributing the mass. So we're changing our rotational inertia, okay? So for part D, what's going to happen is this. We still have to conserve our angular momentum because as she crawls towards the middle, that doesn't provide a torque, right? Because look, if this is the merry-go-round, here's my pivot point. As she crawls towards the center, the merry-go-round pushes her towards the center and she pushes the merry-go-round out. That doesn't provide a torque, right? Because it's right along your lever arm. The forces are parallel with your lever arm. Okay? So we're going to have the total angular momentum before she began crawling, which notice is still this, is equal to the total angular momentum after she crawls to the center. Okay? So the left-hand side of my equation is still this. So we're going to have 53.5 equals, well, the angular momentum of the merry-go-round is still going to be 115.2 times some omega, plus the angular momentum of Sally. Well, it's still this, except her radius has changed now, right? Because now she's, instead of being at the very perimeter of the merry-go-round, her radius isn't 1.2 anymore, it's just 0.6, right? So 40 times 0.6 squared times omega, okay? And solve that, all right? I'm going to skip the algebra because you guys can clearly do that. And so what we find is our angular velocity increases, just like the figure skater, right? Okay, because she pulled her arms closer to the center, right? Okay, but it turns out her linear velocity actually decreases because if you do omega r, if you do 0.416 times her new radius of 0.6, it turns out to be only 0.25 meters a second. So curiously, although she spins faster angularly, her linear velocity decreased. Okay? All right. So we should probably do one last example here. When we did regular momentum, we did these sort of ballistics problems. Oh, I'm not going to get into all this gyroscope stuff. If there's time right before the AP test, I'll talk about it. Worst case scenario, there might be one multiple choice question about it. And we are tight on time, so I'm going to not worry about that. Yeah, I don't think I've ever seen a question about it on the thing. Oops, and All right, there we go. Okay, so here we go. Last example. All right, so here we've got a meter stick that's hanging suspended from one end. So here's your meter stick. All right, and it's hanging suspended from one end, so you've got this sort of pivot point so that the meter stick can kind of swing back and forth like this, okay? All right, and so what we know is that the mass of the stick is 0.09 kilograms. We know that obviously it's a meter stick, so it's 1 meter long, right? So I, for a uniform rod, is 1/3 mr squared, where r is the total length. You know, let me use L, because r is going to end up being something else later on. So let's use 1/3 ml squared. So it's 1/3 the mass. Oh my gosh, my pen isn't listening to me. So it's 1/3 the mass times 1 squared, so you get 0.03 kilogram meters squared, okay? All right, so that's that. It's hanging there, all right? Then you've got this glob of clay. Sorry, that was a gross noise. So the mass of the clay is 0.05 kilograms, and it's fired at 4 meters a second, and it strikes and sticks to the 50 centimeter mark, okay? So the question wants to know what angle the meter stick what angle will the meter stick swing? Oh, this is a terrible sentence. What angle will the meter stick make with the vertical when it stops and swings back down? Okay, so the clay is going to hit the thing, the meter stick's going to swing up and come back down. Okay, so the first part of this honestly is very similar to the merry-go-round problem because we've got this collision, but then there's also after the collision there's some conservation of energy, right? And then this last part deals with impulse and change in momentum, okay? Or angular impulse, I guess is what it would be called there, okay? So here is the deal. So what we have then is our total angular momentum before the collision has to equal our total angular momentum after the collision. So the angular momentum of the meter stick before the collision plus the angular momentum of the clay before the collision. Initial has got to equal the angular momentum of the meter stick after the collision plus the angular momentum of the clay after the collision. So 0 for the meter stick before the collision. Angular momentum for the clay, we can just do MVR, right? Because it's a point particle. So our M is 0.05, V is 4, the radius is 0.5, right? Because it's just half of the meter stick. Okay, that's got to equal the angular momentum of the meter stick afterwards, so that's going to be I omega oops, plus the angular momentum of the clay afterwards. So again, I want the angular momentum, so I'm going to treat this now as a point particle. So I'm going to do mr squared. So m is 0.05, r is 0.5, roughly square it, times omega. Oops, this is 0.5. Okay, so mvr equals I omega plus I omega is basically what I did there. Okay, so solve for your omega, and it turns out to be 2.35 radians per second. Okay? So that's the angular velocity immediately after the collision. That means we've got some rotational kinetic energy, right? So let's do this. Oh, not what I wanted to do. Oh my gosh, why does the smartboard hate me today? Okay, so the rotational kinetic energy then is 1/2 I omega squared. So 1/2 times I. Well, what is I? Well, the meter stick has rotational inertia, and the clay has rotational inertia. Meter stick plus clay. So that's our I times omega squared. So the rotational kinetic energy then turns out to be 0.117 joules, right? Because it's rotational kinetic energy. All right, so that's the rotational kinetic energy immediately after the collision. And so the idea is our meter stick is going to swing up. I don't know why I'm making all these gross noises today. All right, and so at the instant it stops, we're going to have GPE, right? So fortunately, because the clay is right at the middle, we can look at the, we haven't changed the center of mass, right? The center of mass of our system is still at the 50 centimeter mark, right? So this is going to equal the GPE at the point at which we stop, so that GPE is our combined mass. So that's the meter stick was 0.09 kilograms, plus the clay was 0.05 kilograms, times 9.8 times H. So solve for your H, and you get 0.08 something. Shoot, I'm sorry, I don't remember what it is. 86, there we go, sorry. Meters, okay? So that's how far this went up. So now I've got this little triangle here. So my hypotenuse is the 0.5 meters, half a meter stick. If this distance is 0.086, then this distance must be 0.5 minus that. So that turns out to be 0.414. So now I can just do inverse cosine of that. So my angle with the vertical is the inverse cosine of 0.414 over 0.5, and it gives you pretty close to 34 degrees. Okay? And we're almost done. Question B says, if the collision lasts 0.02 seconds, then what average force does the clay exert on the meter stick? So, here we go. So I think that I can, come on, computer. Oh, I know, here we go. There we go, okay. So the idea then is this. So it's about force, right? So change in momentum is net force times time, but this problem isn't about linear momentum, it's about angular momentum. So the angular counterpart is change in angular momentum is net torque times time. And notice the question asked for average, so we can use this, all right? Saying average net torque would be comparable to the net torque being constant, okay? So let's see, our change in angular momentum. Well, that should be change in linear momentum would be mass times change in velocity. So we want I times change in angular velocity. All right? Of the meter sticks, that's equal to our net torque times time, right? Oh, well, this is not bad. So let's see. So I for the meter stick, right? We're trying to find the net torque on the meter stick, so we want to use the rotational inertia of the meter stick. So that was 0.03. Immediately before the collision, our angular velocity is 0, and immediately after the collision, the angular velocity is 2.35. So we're looking at 2.35 equals the net torque times that 0.02 seconds. So if you solve that, the net torque that the clay provides to the meter stick is 1.41 Newton meters. And so then you can go, oh, well, I know that net torque is force times lever arm, right? So 1.41 equals the force times, well, the gum, the clay, if I'd said gum before, the clay hits the meter stick at the 50 centimeter mark, so our lever arm is 0.5, right? So divide, and it gives you, oh, good, I'm glad I just did that, my answer on the sheet is wrong. So that gives you, what, 2.82 newtons, right? There we go. Woof! Chapter 2, chapter 12 rather, 2 really long videos. I'm sorry. Big concepts. All right, there we go.